This is your presenter Asloob Mudassar, and I am presenting slide number 77 of the course on laser physics. Question is, discuss multi-layer dielectric coatings. How can the coating layers be used to enhance or to suppress the reflections? Also discuss the relevant power reflectivities. The answer is, to coat a substrate, a glass plate for example, that is we want to use glass plate as a substrate with a given dielectric material. The material is evaporated in a vacuum chamber and a specific thickness of the dielectric layer is deposited and later on condensed. So this process is done on a substrate, that we are given a dielectric material and we evaporate that material in vacuum chamber and a specific thickness of that dielectric material is deposited, for example in this case on the glass plate, and then it is condensed. If a substrate is deposited with many such layers of different dielectric materials, the final product is regarded as a substrate with multi-layer dielectric coatings. These dielectric coated layers are usually transparent at the designed wavelengths, for example lambda naught. But of course, since there is some tolerance, so lambda naught plus minus delta lambda, and should withstand high beam intensity. So you see that here we have given two requirements, that is the dielectric coatings, multi-layer coatings should be transparent at the designed wavelength, and the second is that such a coatings should be able to withstand high beam intensity. In the given wavelength range, the dielectric materials must have minimum absorption. In some wavelength regions, for example middle to far infrared region, metal coated, for example gold coated copper mirrors may be appropriate due to their minimum absorption and due to their ability to withstand required high intensity values. So you see that this is the range, that is from the middle to far infrared, where we can use metal coated materials, that is we can, for example we can have a gold coating on copper mirrors. Consider lambda naught as the designing wavelength for a glass plate of refractive index Ns. Here S stands for the substrate and N stands for the refractive index. So Ns is the refractive index of the substrate. So consider lambda naught as the designing wavelength for a glass plate of refractive index Ns. Let us assume that a layer of dielectric material of refractive index Nh is greater than Ns. So you see that we want to, let's assume that a layer of dielectric material of refractive index Nh. Here you see that Nh is greater than Ns. That's why we have called it H, because H means higher, Ns means higher refractive index. It means greater than the refractive index of the substrate, and we are using the thickness of that material to be equal to LH. Of thickness LH is deposited on the substrate. The thickness LH should be such that the wavelength lambda naught reflected from the NH-NS interface back into the NH region is delayed in phase by pi after traveling the region NH with respect to the phase of the light before entering the NH region. So you see that we have a glass plate, we have first coating on that one, which is called the substrate coating with the refractive index Ns, and we have another coating on that substrate, on that layer of refractive index Ns with a refractive index Nh, and the thickness of Nh is LH, small LH, and this thickness is chosen in such a way that when the light will enter into this material and reaches at the interface of the NH-NS, a phase shift of a phase, then it is reflected back from that surface. So the total distance, which is 2 LH, is traveled into that thickness. that is into the refractive index of NH. A total thickness that is traveled in this material is 2 times LH. and we want that this thickness should be such that a wavelength of desired wavelength lambda naught when entered and leave that material will suffer a phase shift of pi. Now consider a second layer of some other dielectric material of refracting index NL less than NH. So you see that we have another coating with a refractive index NL. NL means that a material with a low refractive index. That's why we have labeled it with the subscript capital L, standing that it is a low refractive index material in comparison with NH, and of course NL is less than NH on top of the first layer. Suppose that the light of a wavelength lambda naught enters the NL layer to the NH normally. So you see that here we are considering normal incidence from a material of refractive index NL to a material of refracting index NH. The light will be reflected at the NL-NH interface back into the NL region, undergoing a phase change of pi. So you see that here the light is entering from a refractive index of a low value to a refractive index of a high value. So a phase change at the interface will occur, because the reflection at the interface will also accompanied by a phase change of pi at the NL-NH interface. The same light when reflected from the NH-NS interface will be reflected back into the NH without undergoing any phase change, because the material NS has a lower refractive index in comparison with the NH material. So at the NH and NS interface, due to this boundary, the reflection occurring at this boundary will not undergo, the light will not undergo any phase change. When this light will enter into the NL layer, it would have undergone a phase change of a pi due to the light has traversed a width equal to 2LH. So you see that due to the thickness of this LH material, which is 2 times traveled by the light, when it gets back into the NL material, then the light would have traveled a distance of 2LH, and this 2LH is chosen in such a way that a phase shift of a pi is produced. The two beams reflected from the two interfaces into the NL layer will be pi shifted and will add constructively to produce intense reflected beam. The two-layer dielectric interface for enhanced reflection is shown in figure 77.1, that is in this figure. So let me read the caption: two layers dielectric interface for enhanced reflection. Two layers mean that excluding the substrate coating, we have two coatings actually. So this will be called, apart from the substrate, it will be called a dielectric interface, two-layer dielectric interface, because one interface will occur at the NH-NS boundary, the other interface will occur at the NL and NH boundary. So there are two interfaces. That's why it is called two-layer dielectric interface. Basically these are three coatings: NS coatings due to NS, coatings due to NH, coatings due to NL. So these are three regions, and these three regions form two interfaces. One interface is the NH and NS interface, the other is the NL and NH interface. So you see that the thickness of the NH material has been shown to be small l with a subscript of capital H, that is LH, is the width of the thickness of the material having refractive index NH. So the thickness of the NS material is not important. Similarly, we have shown an indefinite thickness of the NL material, because here the thickness of the NL material is not also important, is not important. But later we shall show that this could be important when we are using such a material as in the laser, as a laser cavity. So we have also shown the NH material, NH layer, and also the NL layer on the side of this, on the right side of this figure. You can see that there are two phi. We have shown phi 1, which is when the light is reflected from the NL and H interface, then the light which is reflected from the top, that is from this interface, will undergo a phase change of a pi. because the light is hitting at a boundary which has a refractive index greater than the refractive index of the NL material. Because NH is greater than NL, so a phase shift of pi is produced. Now look at the phi 2, which is also equal to pi, but this phi is not due to any interface, but it is due to the distance that the light has traveled twice within the NH material. So when the light from NL to enter will when the light from NL material enters the NH material, the light will, and then of course from the light will be reflected. We are considering the light which is reflected from the NH and NS material. You see that here the phi 2, we are actually talking about the phi 2 which has traveled a distance of 2 times LH within the NH material. So the phase change at the first interface, that is the NL and H and NH interface, has been shown as phi 1. Now this phi 2 is due to the distance that the light will travel within the NH region equal to 2 times LH. So when the light will hit the NH-NS interface, there will be no phase change, because the light is because the interface at the interface NH has a refractive index which is lower than the NH. So no phase due to the reflection will occur at this interface, but the phase change that will occur is due to the light that has traveled a distance 2 times LH in this material. So when that light gets back into the NL material, it would have gone a phase change of a pi due to the distance it has traveled in the material of refractive index NH. So we have shown phi 1 is equal to pi, and similarly phi 2 is also equal to pi. So these two lights which have undergone the same phase change will interfere constructively, and due to constructive interference the intensity will increase. And you see that I have also shown NH and S interface and NL and NH interface. The two interfaces has also been shown. The thickness of the NH layer in figure number 77.1 can be calculated using the equation phi 2, which is the phase change when the light has traveled a distance of 2 times LH. So phi 2 is equal to k. If you want to calculate the phase, you have a k multiplied by the physical length, which is 2 LH. So k is actually 2 pi over lambda, and the designing wavelength is lambda naught, so we have 2 pi over lambda naught, but we are using also with the lambda naught as a subscript, but we also using NH as a subscript with lambda naught, because NH means that this lambda has been designed for the refractive index, which is NH refractive index. So we are designing, this is lambda naught is the designing wavelength, and this designing wavelength is the designing wavelength, and when it enters the material NH, we have to label this designing wavelength with NH also. And you know that now we are multiplying it on the right hand side by 2 times LH. Now lambda naught NH is equal to lambda naught divided by NH. So lambda naught divided by NH, so NH will move into the numerator, and then we have 2 pi NH over lambda naught. And you see that here we have removed the subscript NH because we have used lambda naught NH is equal to lambda naught over NH, and this NH now will move in the numerator, and we have 2 pi NH over lambda naught, and then of course multiplied by the 2 NH. So we want this quantity to be equal to pi, because we want that the phi 2 which has undergone, that the phi 2 is equal to pi, and this is due to the traveling of the beam into the NH material twice the length length LH. So that's why we wanted to set it equal to pi. So solving the length LH from equation number 77.1, we get LH is equal to lambda over 4 times NH. So you see that the thickness of the material having a refractive index NH should be equal to lambda naught divided by 4 times the NH, 4 times the refractive index of the material. So setting up the width of that material having refractive index as nh equal to that given by equation number 2, we can produce a phase shift equal to pi when the light will travel into that material and will be reflected back into the NL material, into the NL region. Such multi-layer, for example 2 layer in our case, coatings can be used to enhance reflection, because the 2 lights which are reflected from the which are reflected parts and has a phase of phi 1 equal to pi and phi 2 equal to pi will interfere constructively, and due to that constructive interference that will enhance the reflection. In figure 77.1, the thickness of the NL region is much greater, and the region may be considered to constitute the optical or the laser cavity. The 2-layer dielectric interface as shown in figure 1 can thus be considered as one of the reflectors of a laser cavity. So you see that if we are using this material as a laser cavity, then you see that one end of the laser cavity will be due to the NL, NH and NH-NS interface, and the length of NL will form the length of the cavity. The length of the NL material will form the length of the cavity. And of course we can use at the other end, that is at the top face of NL material, some coupler, output coupler for the light, for the laser light to come out from that region. So the 2-layer dielectric interface as shown in figure 77.1 can thus be considered as one of the reflectors of the laser cavity. So that's why we have not imposed any limit on NL. And in our analysis there should be no limit on NL, because NL could be of any length, because we want phi 1 to be equal to pi and we want phi 2 equal to pi, and that has been achieved using the LH length equal to lambda naught over 4 pi NH as given in equation number 2. So you see that this length does not involve any calculation involving the refractive index NL or the length of the region of the NL material. If a layer stack starts and ends with a dielectric coating NH with alternating layers of NL coatings, that is total number of coated layers is odd, say J, capital J, and J is an odd number due to odd number of NL coatings alternatively between the NH materials, then the total power reflectivity at the designing wavelength lambda naught is given by the expression, that is the total reflectivity R as a function of lambda naught is equal to the square of NH raised to power j plus 1 minus NL raised to power j minus 1 multiplied by NS, and this whole divided by NH raised to power j plus 1 plus NL raised to power j minus 1 multiplied by NS as given in equation number 3. We are not proving equation number 3, but we are just taking it as granted. That is the power reflectivity for multi-layer stock which starts and ends with a dielectric coating NH and with alternate layers of NL coatings. And if NL coatings are odd in number, having J as the number, then of course this is the formula that can be used to calculate the reflectivity. R of lambda, that is any wavelength other than the designing wavelength lambda naught, we call that reflectivity as R of lambda. So here R of lambda will be less than R of lambda naught, and a high reflectivity is meant only for lambda is equal to lambda naught. Plus we can allow a tolerance of plus minus 10% of lambda naught. Because lambda naught is a very strict number, we must have some tolerances with that one. So this lambda that we can allow in our calculations should be that lambda is equal to lambda naught plus minus 10% of lambda naught. So with this lambda we can say that R of lambda is less than R of lambda naught. As capital J increases, the peak value of R of lambda naught increases and the width of the region R of lambda expands in lambda. So you see that if you have increased number of multi-layer dielectric materials, then of course you improve the peak value of the R of lambda naught, but at the same time the spread of R of lambda will increase. To reduce reflection, that is to produce anti-reflection dielectric interface. For example, sometimes we need in optical systems an optical component should have an anti-reflection coating so that the transmission could be maximum and the minimum reflection. Such dielectric materials can be used as output laser coupler, because there we want to enhance the transmission power of the laser system in a controlled way, and we want to, for example, minimize the reflection. So we can, or for example, in other places you can also use such anti-reflection coatings. For example, when you are designing a camera lenses, such anti-reflection coatings can be very useful. So to reduce reflection, that is to produce anti-reflection dielectric interface, a two-layer dielectric surface with anti-reflection coating is shown in figure number 2, where we have NS highest refractive index, then the lower one is NL1, and further lower is the refractive index with the region NL2. So we have now over here 3 regions: NS region, NL1 region, NL2 region. But you see that here NS is greater than NL1 and NL1 is greater than NL2. But you know that this differs from our previous case in that the NS was smaller than the middle layer, which we called as NH layer. But here we have called it as the NL layer because its refractive index is less than the refractive index of the substrate material. So this is the difference. It means that when the light will hit at the interface, that is NL1 and NS interface, it will due to a greater refractive index beyond that region, the phase change of a pi will occur. So pi phase change will occur due to the interface, and the pi phase will also occur due to the light being traveling in the region of length as designated by small l with the subscript capital L1. So one is due to the interface boundary phase equal to pi, and the other is due to the traveling of the wave in this region. So a total change of 2 pi will occur. So that's why we have used pi is equal to 2 pi. Phi 2 is equal to 2 pi, and phi 1 is equal to pi as before. So that's why you can compare over here that in this region phi 2 is equal to pi, because our NS region has a smaller refractive index compared with the NH region. But you see that here the case is different. We have NL region has a smaller refractive index as compared to the NS region. So an additional phase change due to at the interface will occur due to greater refractive index of the NS as compared with the NL1. And one phase change is due to the distance that the light will travel in the central region of refractive index NL1. The rest of the things are the same. So when the light due to phase phi 1 and due to phi 2, you see that would differ in a phase change of a pi. So that will destruct each other. So there will be a destructive interference in the region NL2. Due to destructive interference in the region NL2, of course there will be a cancellation, and a light will be, and the reflection back into this region will be much smaller. To reduce reflection, that is to produce anti-reflection dielectric interface, a two-layer dielectric surface with anti-reflection coating is shown in figure number 2, where NL2 is less than NL1 and NL1 is less than NS. And I have explained this diagram, that how the phase phi 2 is produced and how the phase phi 1 is produced, and then of course these two differ in a phase of a pi, so destructive interference will take place, and so the reflected beam into the NL2 region will be much smaller, or will be near zero. Reflection from the NL2 to NL1 interface produces a phase shift of phi 1 is equal to pi in the reflected beam back into the NL2 region, whereas the reflection from the NL1 and NS interface produces a phase shift of pi in the reflected beam back into the NL region. The thickness of the NL region is such that the light traversing this distance twice and returning into the NL2 region suffers an additional phase equal to pi. When this light enters into the NL2 region, it would have suffered a total phase shift phi 2 is equal to 2 pi. Thus, the two reflected beams traveling in the NL2 region are out of phase by pi. That is, phi 2 minus phi 1 is equal to pi. That is, the two beams will act destructively, resulting in reduced reflection. If NL2 is equal to 1, the power reflectivity is given by the formula. So, R of lambda naught is equal to the square of ns minus NL1 square divided by the ns plus NL1 square. Okay, so the thickness of the first dielectric layer in figure 2 is given by replacing NH in equation number 2 by NL. So you see that if you want to find out the thickness of the material NL1, that will produce a phase change of pi when the light will travel in this region. That length is calculated similar to the length that is calculated that we have calculated for the NH for the material having refractive index NH. So similarly, replacing NH by the NL1, we can find out the thickness that would produce a phase change of equal to pi. So the length of so the thickness of the length so the thickness of the length L, capital L1, that is the thickness of the region NL1 is given by this formula. So so the thickness L in the region NL1 is equal to lambda naught over 4 times NL1 as shown in equation number 5. We have ignored multiple reflections in the substrate material and in the first layer while discussing the physics relevant to both the figures. You see that here we have not taken into account the multiple reflections, because when the light will enter, for example, this arrow downward, when the light will enter into the region, for example, the region with the refractive index NL1, multiple reflections may occur in this region. And the light from each reflection, the light will enter into the NL2 layer. And similarly, when the light will enter into the NS region, multiple reflections will also occur in this region, and multiple reflection back into NL1 and also into the NL2 region will occur. We have ignored the multiple reflections and we have considered only single reflections for the sake of simplicity, because that would serve our purpose in order to explain the coatings for the enhancement of reflection and the coatings and the dielectric layers to minimize the reflection or to produce the anti-reflection coatings. So that would serve our purpose if we don't consider even the multiple reflections within both materials. That is, in this region, in this figure, we have also ignored the multiple reflections in the NH region and in the NS region, and similarly we have ignored the multiple reflections in the NL1 and NS regions. So with that one, we have explained the enhancement of the reflected signals and also the minimization of the reflection signals using the coatings and the structure that we have explained. So this is the end of slide number 77.